Hey folks, it's Miss Stryker here. I was grading some labs today and I wanted to do a little clarification with linearization and why it is so important to linearize. So here's some bogus data that is very similar to your pendulum lab. So on the left-hand side, I see a bunch of lengths. I see 3 trials for each length. I see that the period was, or the time was for 5 cycles. And so then looks like this person divided by 5 to get the period. And so I've got a bunch of lengths and a bunch of periods. And I plotted the length versus the period. And I thought I would talk to you first about why I would notice that this is not linear. How do I know that this is not linear? Just by looking at the graph or looking at the table. And so one way to know that it's not linear is to look at what happens as you go from one point to the next point. So here I've got one point to the next, and I notice that all of the rest of these points are below my ruler. They're not scattered above and below, they're below the ruler. And as I go again to the next point, they're still below the ruler. They're still kind of below. Whoops, I don't want to draw against the ruler. But if I sketch that, they're below the ruler. They're staying below the ruler. So here they are, sort of down here in this region. And again, if I do this again, they're still below the ruler. There's not a scatter. When I get to this last one, oh, look, they're always sort of below the ruler. So there's a curve to that. You can actually see that in the table of values as well. So if you come up here and you look at the increase in length, 20 centimeters, 20 centimeters, 20 centimeters, 20 centimeters, 20 centimeters. It's always going up by 20. But look at the period. Here it's going up by 0.3. Here it's only going up by 0.2. Here it goes up by 0.2. Here it goes up by 0.2. That's pretty consistent. Uh-oh, now it's going up only by 0.1. All right, so that's why you see this sort of curve that is actually more indicative of a square root curve than a linear quantity. So you can see that pattern in the table. You can also see it in the graph of length versus period. And, really, if you think about how the period relates to the length, you have this on your formula sheet. This is given to you on your formula sheet. And you can rewrite that and split the period and the length apart from everything else, because what you've got in your table is period and length. And so if you want to know how they're related, rewrite this formula just using some algebra to separate the period and the length. And then just verify for yourself that all of the rest of this is a constant. 2 pi is a constant, gravity is a constant, the square root of gravity is a constant. So this is kind of like saying y is equal to some constant times the square root of x. It should be looking like a square root curve, and in fact it does, okay? And so I know that it's not linear. And so why would I want to use a plot of a linearization to find something out, to find, for instance, G? In this lab, you were asked to use this linearization to find G. And so let me just clean this up a little bit because I just made a mess out of it. I'm using OneNote, which is a great little app. Helps you to create notes in color, and you can have as much graph paper as you want. And today I just found that there was a ruler, which is great. I hadn't known before that there was a ruler. In any case, if I want to use a period of a pendulum in order to approximate gravity, to approximate G, I see that G is in this equation here. And so I could rewrite this like this. And if I plotted t on the y-axis and the square root of L on the x-axis, then all of this stuff would be the slope. So the slope would be equal to 2 pi divided by the square root of g. And I could work with that. On the other hand, many people plotted, squared everything and plotted period squared. So let's just do that. So if I square everything, I have to make sure, in order to keep this equality preserved, I got to square everything here. So this becomes squared. 2 squared is 4, pi squared is pi squared, and the square root of L over G is L over G. All right, so I've squared everything. I haven't changed my equation at all. It still is a valid equation. Now I'm going to separate the variables like I showed you over on the right. I'm going to separate the variables. So t squared is equal to 4 pi squared divided by G times L. Now, the variables that I've got as my dependent and independent variable are these, right? Those are the two variables in my table. In fact, I'm changing the length. So this is the independent variable. And later I'm measuring the period. So this is the dependent variable. Everything else is constant. So if I plot this on the y-axis, y, this is just a constant here, times L, times, this is going to be like L. If I plot the period squared on the y-axis and I plot L on the x-axis, everything else is just a constant. And I should be able to use that constant to find G. All right. And so let's take a look at this graph. I've already plotted period squared versus the length. So how do I know that this is linear? Well, now if I do the test that I did before, using my ruler to line up points, here I go to the first 2 points. It looks like the rest of the points are below the ruler, but now some of the points are above the ruler. Now a bunch of them are above the ruler. Now they start to look below the ruler. So they're sort of more scattered. It definitely looks like a better line. All right. So now I'm going to actually use my scatter plot to draw a line of best fit. I'm going to scatter the points above and below, and I'm just going to draw a line. All right. Dun, dun, dun. Let's move this off the grid. So now I've got all of these data points. They refer to my data, but I also see that this line, if I were going to find an equation for this line, I might want to use some points on the line that are really easy to identify. So this looks like, what is that? 1.4 meters, 1.4 meters. And if I trace all the way over, I think it's right about there. So the y value is 5.5 seconds squared, 5.5. And I've got this point down here, and what is that? 0.1 meters and 1 second squared. So I can do change in y over change in x. What does that give me? 5.5 minus 1 is 4.5. 1.4 minus 0.1 is 1.3. There's my change in y over change in x. Well, what does that really mean? It's the period squared divided by the length. So now come back down to your formula here. Well, period squared divided by length, the slope should be 4 pi squared over g. So k is really y over x. That's really t squared over L. And for me, on my line of best fit, that's 4.5 divided by 1.3. All right. Well, what is that really equal to? It's equal to all of this stuff. So 4 pi squared divided by g equals 4.5 divided by 1.3, according to my calculation. So could I solve this for g? I could. G would be equal to 4 pi squared divided by what? 4.5 and times 1.3. So I really just cross multiplied here. Okay. And that should give me a pretty good approximation for G using my line of best fit. Now, why is that an advantage over using one point? And Bridget, this is what I was trying to get at. Why is it better to use the line than to use one particular point? Look at each of these points. This point is a little below the line. This point is on the line. This point's on the line. This one's a little below. This is a little bit above. This one's a little bit above. This one's a little bit below. This one's a little bit below. If I use my green line of best fit, my errors get scattered up and scattered down, a little bit down and a little bit up, a little bit down here, a little bit up here. I'm not making use of just one data point. I'm making use of every data point. This line that I've drawn approximates the error by scattering it on both sides of the line. So I get a better line of best fit if I use all of the data, and that means try to make sense of the slope. So for me, the slope is t squared over L, and I know t squared over L is the same as 4 pi squared over g. And if I set my slope equal to 4 pi squared over g, and I use that to solve for g, I get a really good approximation for g using all of the data, not just using one point. I mean, you could use one point. That's what I saw people doing. What does that look like? That looks like, oops, take one of your data points, so 1.69 and 35 centimeters, 1.69 and 35 centimeters, okay, 1.69 squared is equal to 4 pi squared over g times 0.35. Sure, that'll give you an approximation for g, but that's only using one data point. That means you've wasted all of the other ones. So if you make use of your line of best fit, it averages out all the data, averages out all the errors, and you get a much better value for the line of best fit, much better value for g. Okay, I don't know. I hope that helps. You can let me know if it did. All right. I'll talk to you later. Bye.